The floor is yours, please. Thanks.
For sure. Yeah, so I'll start, and then Al's going to do the middle part of the section, and then I'll wrap up with some closing thoughts. So yeah, thanks everyone for accommodating our times, my time zone. I think I might be the westernmost person here in Victoria, Canada. So yeah, we just wanted to kind of give this overview of some work that we did. We got this paper was finally published this year, and we can give you and share links to the paper later on, but it's actually work that we completed probably about 2 or 3 years ago. And so we just want to share some of the philosophy behind what we did in applying machine learning techniques to numerical simulation, go over some of the technical aspects of how we did it, because partly it was based on software that Al, me, and other members of the team developed in order to actually do online inference within an ocean model. And then just kind of give some of the initial key results that we showed and to describe what we're going to be doing going forward. So the first question I want to just kind of quickly address is like why we wanted to target this idea of predicting eddy kinetic energy using machine learning, as opposed to trying to directly parameterize eddy terms within the dynamics equations themselves using eddy parameterizations. Because that's kind of one of the classes of applications of machine learning that has been done in both computational fluid dynamics, in the atmospheric sciences, and also in oceanography, which is to say, like, okay, let's run a high-res resolution model, and then let's calculate the eddy terms and see, or do the Reynolds averaging and see if we can predict the eddy terms themselves. I think one of the things when we embarked on this kind of project, we were a little bit leery about that because it's very difficult to constrain a machine learning model to be able to predict and, conserve momentum, conserve energy, and all those kinds of things that we hold near and dear when we're trying to solve these equations numerically. So instead, one of the things we looked at was this idea of like, can we predict eddy kinetic energy, right? And there's all sorts of theory out there that shows how you can kind of like take the Reynolds average Navier-Stokes equations and then transform them into something that looks like energy-like quantities. And then by doing this, you actually get something that looks fairly useful in terms of understanding how turbulence mediates the flow of energy between kinetic energy, large-scale kinetic energy, turbulent kinetic energy, and available potential energy. So in particular, there's this term here, right, this W prime B prime term, which the famous Jet McWilliams, 1990, right, shows that there's a way you could kind of parameterize this as isopycnal diffusion, thickness diffusion. It's an overturning by eddies there. And so in this particular set of equations, it's nice because you can directly see the transfer of energy between the turbulent eddy kinetic energy to the available potential energy there. The other thing that's really nice about eddy energy is that because it just pops out of the Reynolds averaging, right, you can actually it's well defined at all scales of modeling, right? So it always represents this unresolved subgrid scale term. And you can then relate it to diffusivity via some scaling arguments, right? So there's classic kind of like Taylor scalings. I think Julian Mack recently proposed, with David Marsh proposed a new way of doing it, to add some other length terms or timescale terms to it. But essentially, you can say if you have an estimate of the eddy energy, you know that it should be proportional to diffusivity in some way. So that's either something like the GM diffusivity, or that's something like tracer diffusion, right? So it's a nice, convenient quantity. Plus, we understand the concept of energy a little bit better than we might understand something like a direct parameterization of momentum flux that a machine learning model might predict. But one of the big open problems, even if we have this very nice theoretical framework in which to work with eddy kinetic energy, is how do we actually calculate it, right? There were some animations here that I forgot to do. So here is actually, so this is just taking that one equation that I showed in the previous slide that is directly related to the eddy kinetic energy itself, right? And so you've got all these terms here. You've got 5 terms on the right-hand side. And in some way, you need to either make a determination that you can either directly calculate it, you have to parameterize it, or you have to just ignore it, right? And so in practice, this was what was done by Jansen et al. So they did the W prime V prime term as an energy sink term from GM. They took this phi sub k term from the lateral viscosity, and then this x epsilon k and this del dot j prime term, they associated with Laplacian dissipation with kind of just like a coefficient there, and also bottom drag. And then lastly, for the turbulent pressure work, they just kind of they just completely omitted the term, right? And so these are really difficult in a number of ways because to actually calculate this, because as you can see, there's two things here, the GM and the lateral viscosity, which are actually parameterized themselves, right? So, and this equation, because it's a result of these parameterizations and some ad hoc coefficients, there's a lot of tuning that actually has to go into this. So it's not quite clear. And, this is one of the goals of the eddy energy CPT of the United States, which is to get better bounds on each of these terms and to see like where the errors are creeping in when we take this kind of approach. So we kind of figured that this was ripe for machine learning, right? Because we know that the eddy kinetic energy should be related to the resolved fields in some way. And so from the get-go, we tried a number of things to say like, okay, well, what do we think could be good predictors of eddy kinetic energy? So one of the requirements that we had were that they were rotationally invariant, right? Because we have, especially for global grids, we can't guarantee that they are orthogonal to northeast, southwest directions. We wanted to figure out if we could build in some kind of scale dependence on it. And so we eventually settled on these kind of 4 features. And so what's actually shown up here is actually a sub-mesoscale resolving simulation. And you can see this kind of wealth of turbulent field that's all in here. And the 4 features that we eventually kind of decided on that we thought would be representative was vertically averaged isopycnal slope, right? Because if you have steep isopycnals, then you have more energy for the mesoscale field to develop, relative vorticity, mean kinetic energy, and then the Rossby radius of deformation. And then the last one here was thrown in to basically try to get some sense of if we could build in scale awareness, right? To say okay, if the eddies are well resolved, maybe we get a machine learning model to actually predict the fact that it doesn't need to predict eddy kinetic energy. So then we built a machine learning, an artificial neural network, which Al will go over in terms of how we did that, to predict eddy kinetic energy. Al did a lot of the training and validation for that part of it. And then we just used the existing Janssen et al. Framework for prognostic eddy kinetic energy to get us a GM coefficient. And we plugged that GM coefficient into the parameterization that was existing in MOM6. So that's basically our idea here, right? It was okay, we know that the prognostic eddy kinetic energy equation has a bunch of unconstrained terms. So so the EKE that is generated, we are unsure of its accuracy. Whereas if we have enough data, we felt like we could figure out to build a machine learning model to actually predict the eddy kinetic energy and get us a better estimate of it. And so I'll hand it off to Al to talk more about this since he, like I said, did most of it. So yeah, take it away, Al, then just let me know when you want me to advance.
Okay, thank you. Yeah, so when we started working on this problem, one of the things we wanted to do was to train the model on a high resolution grid, so 1/10 of the degree nominal grid resolution, and then to apply the model on a lower resolution, right, on 1/3 or 1/4 of a degree nominal resolution. And so we had to train the neural network based on data produced on the 1/10 of the degree model, where we actually can resolve eddy kinetic energy. And so we could have a target for a neural network to train on. And so we trained it offline, right? So we gathered a bunch of data points from a few years of simulations with MOM6 and 1/10 of the degree model. And then we just basically took every data point and make it just a single point in the data set. So we didn't use patches, we didn't use larger areas for predicting the eddy kinetic energy. We only wanted to do a point-wise prediction. And once we identified these 4 features for the EKE prediction, we processed the training data set. So we basically pre-processed it before feeding it to the neural network for training. And so first of all, we identified some features which were more or less log normally distributed, and so we applied the log to them. And then once we had more or less everything looking kind of normally distributed, even though you can see there are some peaks, we widened the data. So basically we normalized it and we made sure that it was okay. As you see, the relative vorticity has a trick to maintain also the sign. And so we had to apply a function, which is described in the paper. It's not so relevant here, but basically there are two log normal distributions, which we make sure that don't overlap. Then obviously, once we had the data set ready, we split it into training and validation subsets so that we could train the neural network and see if the results were agreeing with the validation data set. And one thing which is important to remember is that this part of the pre-processing will have to be performed also at inference time when we will be using the neural network within the simulation. So it means that once we store the neural network, we also have to add this part of pre-processing to the neural network so that we can pass raw data, like the features to the neural network, and the neural network will just compute logarithms and normalization of the input so that it can output the right EK value. And we can go to the next slide, please. And then we had to design the neural network. So we tested several different architectures, starting from a very simple fully connected neural network, and then convolutional neural networks, like plain convolutional neural networks. One of the targets was to try to keep the size as small as possible. And then, like, should we answer questions as we go? Because I see one question, which
I think we can do at the end, so that
okay.
because otherwise it becomes a bit complicated to follow.
Okay, thank you.
For you to follow the talk. Yes.
Thank you. And so in the end, like the idea was to keep it small, and we used residual networks as a final architecture of choice. So residual networks are usually used for images, and since we're doing point-wise predictions, this is kind of strange because you don't really need to do convolutions on one pixel, basically, right? So convolutional neural networks, maybe you know that you slide a spatial filter over your domain, and then you gather the results and you use them to train the neural networks. We actually use transpose convolutions, as you can see on the top right corner. We have the input, and then using transpose convolution, basically the input is blown up to be a 7x7 patch, basically. And then we apply these residual blocks. Residual blocks are the main functional block of residual networks. They are like convolutional networks, so they apply this sliding filter, but they also let the input pass through so that the gradient is actually backpropagated more efficiently, and this gives a lot of improvement on the performance in training time. And also avoid some explosions of gradients or some vanishings of gradients. In the end, we started with a long chain of residual blocks and started taking away some of them. We went to the minimum size we could achieve without then getting nans, so nada numbers, during simulation time or inference time. One important thing is that we needed to pick a particular loss function. So to train the neural network, we couldn't just use the mean square error, right? So if we use the mean square error, since most of the results were in the middle, right? So you can see the initial distribution of EKEs in gray in this picture, and you can see that this is really centered around more or less -5 in logarithm. And if we use just mean squared error, everything gets squashed to the center. So basically we got a lot of predictions in the middle of the domain, basically the image domain, and we didn't get the extrema. So we had to penalize those points in the middle, because as we have less samples, we want them to be less relevant. We have less samples with the extrema of the distribution. So we wanted them to be more important. So we applied a weight to those samples, and we penalize the samples in the middle. And this is our custom loss prediction. So it's not super easy to see this from the images on the bottom, but you see on the left-hand side, you see the real value, the target value. In the center, you see the mean square error loss prediction, and you see that it's quite average. Especially, you don't see a lot of dark blue and bright green. Whereas with the custom loss prediction, we were able to extend a bit the prediction, and you see a bit more bluish domains and bright green domains. And this was a way to really try to mimic the initial distribution and gave the best results then at runtime. And so once the model was trained, we just stored it together with the pre-processing, and we made it available for the simulation at runtime. And to do that, to use the model into the simulation, we applied the library we were developing, and which is called SmartSim. And I will now talk briefly about it to give an idea of why we chose it. So we can go to the next slide. Okay, so why SmartSim? So SmartSim is, first of all, an open source library. So the choice was obviously to make everything in the open source domain so that other researchers could use the library, could apply the same paradigm to their simulations. And it's thought for data in motion philosophy. So it used to, until a few years ago, it used to be so that in HPC, you would just run a long simulation, store all the results on disk, and then maybe open it in a second moment with another software and analyze it, post-process it, and then maybe do something with the results, with those results. But actually now the workflows are becoming more complex, in which you want to basically use the results of a simulation immediately into maybe an AI model or in a data analytics application to post-process them or to extract some features and then feed those features back into another simulation or in the same simulation and so on. So SmartSim was born to exactly allow researchers to do this, to apply this paradigm to their existing libraries. So basically we wanted people to take their old code, the well-established libraries, and just put some calls without having to rewrite all the code and without having to rewrite AI toolkits into their own code, right? So SmartSim basically enables simulations to be used as engines, right? So they can produce data which is then consumed by other parts of the workflow. And those other parts of the workflows could be like machine learning models, like which you could basically plug into Fortran, C or C++ simulations, clearly parallel simulations using MPI, communicate data, right? So with SmartSim, since SmartSim establishes this kind of memory channel between two different simulations, which is our orchestrator, so it's in a memory database, you can actually put data on the database and access it from another simulation, right? So on the bottom of the slide, you see a very simple model where on the left-hand side, we have the simulation, the native HPC simulation. And on the right-hand side, we have, for example, analysis and visualization. In the middle, SmartSim will put this orchestrator, so this in-memory database, which can be used to share data, but also to apply code, so basically apply scripts or AI models to the data you store, so that inference, for example, with our existing model can be done exactly on the database without having to go to another application. And then all different workflows which can be thought starting from this, adding more pieces. There's no limit to the number of applications which can connect to the orchestrator, can be implemented with SmartSim. And this is what we call data in motion philosophy, because data is never still in some application. It's never only written to disk. We do everything avoiding disk writes. And then obviously, once you have to store the final data, you can store it to disk. And we can go to the next slide so we can see quickly. We thought about SmartSim for different HPC domains, right? We thought it for fluid dynamics, for climate simulations, for chemistry, for molecular dynamics, for biology. Obviously, this example you'll see is about ocean simulations. But the idea is that the calls are so generic, the method is so generic, it just works on tensors, so it just works on arrays of numbers. You can apply it in any simulation, in any type of code. And it's very easy to use it because you only need few calls. Like, for example, for the example you will be seeing with MOM6, we had to add to the time step in code, I think more or less 4 calls to SmartSim, plus some setup, which is also very brief. So we try to make it easy for scientists to add these portions of the workflow to their code without having to go and change everything in the existing code bases. And we can go to the next slide. Okay, so I'll show two. Okay, yeah. Basically, the online inference is what we use SmartSim for in this basically in this work we are now presenting and we've published. And so now I'll let Andrew talk about the use case more in particular, but what I want to just say is that, as you see below, there is a PyTorch model. So that's exactly the neural network we trained before. So the idea was that the neural network we trained offline is put on the database, which is set up at runtime, and then it's used at inference time by the MOM6 ocean simulation. And with that, I think that Andrew can conclude their presentation. So,
yep, for sure. Thanks, Al. Yeah, so essentially what we just did was we took GFDL's just off the shelf OM4, 025, their quarter degree global simulation that they used for CMIP6. And then we just, we turned on the Janssen-Null parameterization and we embedded, as Al said, these smart Redis calls so that it could do online inference. And so what you're seeing in the top right there as part of the animation, this is eddy kinetic energy being predicted point by point by the machine learning model at every single baroclinic time step of the model, right? So like one of the things that we were really trying to aim for here was one, to make sure that the simulation remains stable, but then also two, to evaluate whether all this communication over the network and inference would impact the simulation in terms of its time to solution too much. And really it didn't have too much of an issue. I think overall it ended up being like a 1% performance hit. You know, 1 or 2% performance hit. So it was like entirely acceptable given the new capability from machine learning inference that we had added. And to really try to test this at scale, we actually ended up doing 12 ensemble members that ran on 10,920 CPUs and on 16 V100 GPUs. Actually, those are P100s, actually, I think. So we ran it for a full 10 years, and subsequently we've done it for 2 full core cycles, and we see no signs of instability or crashing or anything like that, which kind of validated our initial hypothesis that kind of going, not necessarily directly predicting the eddy terms, but kind of feeding in parts of, feeding in a machine learning inference into a parameterization itself is a fairly safe and straightforward way of integrating machine learning predictions into a motion model. So one of the things, so here's just a quick kind of like snapshot images, or not snapshots, but climatological plots here. So to see what the eddy kinetic energy actually looks like. So one thing to notice here is that the eddy resolving is a 10th of a degree, right? So this we ostensibly think is resolving the mesoscale in most regions, whereas these 2 plots in the middle on the right are both from the quarter degree model. So these are not exactly the same model, obviously, because they have different grids, but they are, you know, the same dynamical core. Yeah, they are the same dynamical core. So as you can see here, Miki on its own doesn't really capture a lot of the elevated eddy kinetic energy in the Western boundary currents. You know, whereas the machine learning predictions do quite a good job of capturing the, yeah, that elevated energy. You know, Southern Ocean, it actually looks fairly similar between the Janssen-Null parameterization here and EKE. But once you start doing the zonal averages, you can actually start seeing where the big differences are between our machine learning approach and the Janssen-Null approach. So one thing is very, very clear is that our machine learning model is over predicting eddy kinetic energy in the tropics, right? And this actually ends up not being that bad of an impact for us because there's a resolution function inside of MOM6 that automatically scales away these parameterizations when you resolve the turbulent field well. And since there is equatorial refinement there, you know, we are resolving those Kelvin waves and tropical instability waves. So this actually ends up not being a big deal. So if you exclude the tropics there, or the regions where the resolution function is active, you essentially get about a 40% improvement over the Janssen et al. Parameterization. And especially in the regions where we are particularly think that we need to be capturing that, right? At the mid latitudes in the Southern Ocean, you can see that both the eddy resolve simulation and the machine learning predictions are essentially falling exactly right on top of each other. whereas Jansen et al. Is significantly lower, shows significantly depressed kind of eddy kinetic energy as compared to the eddy resolving simulation. All right, so this is basically is just a quick wrap up. So like I said, one of the things that we really wanted to emphasize here is that we think that kind of figuring out the places where machine learning predictions can be useful is incredibly important, as opposed to just kind of like just brute forcing it into the dynamics equations, because we can actually control things a little bit better, right? One of the other advantages to that is that because we're still applying essentially these predictions via GM, we actually understand and have much better intuition about the effect of the parameterization, how it might interact with other aspects of the numerical solver, as opposed to saying like, now we're introducing a new term that we don't know is well constrained. We don't know what the errors are associated with that. The other thing is that EK does seem to be a predictable quantity. Obviously, as we showed, as you can see in the last graphs, like, we probably could find some ways to improve the machine learning model. Al and I and the folks that we're working with at NCAR have some ways of thinking about, maybe we can incorporate some time evolution information into it. Maybe we could do something like a convolutional neural network so that we can ingest kind of the neighboring cells. But overall, like, even our first pass with a relatively simple model seems to be doing a fairly good job. One thing I didn't stress before, but I really want to point out here is that, SmartSim is not the only solution that allows you to call, a machine learning model package from Fortran. But one of the things that we do provide, because we're doing all the inference in this centralized database that Al was talking about, is that we don't require that every single node that the simulation is running on also has a GPU, right? We can kind of really pack in all that machine learning inference onto a handful of nodes that the database is running on, as opposed to, having underutilized GPUs on every single compute node. So we've tested this out. So we've scaled out this quarter degree configuration to like 3,000 cores. And we find that something like 4 GPUs is sufficient to do that. So instead of using like, 50 nodes with 50 GPUs, we're using 50 CPU nodes and only 3 GPUs. So it actually allows us to do the things and use the resources that we have available. This is the Smart Redis and SmartSim integration has been implemented fully in MOM6. We're part of the main trunk at this point. We're talking with folks in M² Lines, particularly Alistair and his postdoc, about how to, more broadly use this within the MOM6 code base. We've done some initial testing, and we find that the base OM4 quarter degree model without parameterization still, does overall a better job. So now we're moving to a new experiment where we're testing this machine learning prediction in the half degree model, which does include GM already by default, to see whether these the improvement in eddy kinetic energy actually makes the overall simulation more accurate as well. In terms of NEMO development, we have slated this to work on it a little bit more closely in the next quarter or two. So this is largely work that I'm doing to really kind of figure out the right places to include Smart Redis into the NEMO build, making a new module for NEMO so that others can also initialize and access the same Smart Redis client. But as Al said, like, a lot of this code is actually relatively small. If you look at the implementation that we did in MOM6, it's probably something about 120 lines of code, 80 of which is just calculating these features. So, maybe 40 lines of code related directly to SmartSim. So it's not going to be a very big module, but should be fairly accessible to large ones. And then ongoing, we've been talking with Anastasia, who's got, I think she mentioned in her intro slide, or in her intro a couple meetings ago, that she's working on a machine learning model to do these nonlinear EOS corrections. And I think that that's what I'm at least targeting to be the first kind of demonstrator of SmartSim and online inference for NEMO. So with that, we'll close out and we'll take any questions.
Thank you very much, Andrew and Alessandro. So I really like that you merge technical, scientific description, also the way you develop your your work. There were already some questions in the chat that were already answered, but perhaps we can go first through them and then leave to other people. So Julie asked whether the reconstruction of eddy kinetic energy was barotropic, and Andrew answered yes, but maybe you want to say something more, Andrew, about that, please.
Sure, yeah. So I mean, we essentially did the vertical averaging, right? So it is more akin exactly to what Jansen and all did. We have been talking, well, so the MOM6 community has been talking about whether it makes sense to try to calculate EKE like level by level, or figuring out the right vertical function to apply and scale like a kappa GM estimate from a vertical average one. So I think that's an open question that we're tackling right now in terms of, is it sufficient to do vertical averaging, especially since MOM6 is a general coordinate model, so you can get it some very thin layers, like what makes more sense. And so far, I think we kind of think that we can control things a little bit better by doing the vertical average EKE and then applying a resolution function.
Okay, thank you, Andrew. And then there was another question by Redouan, whether the training validation splitting of the data was done spatially or temporally, or both, perhaps. So if you can say, I think you answered already somewhere, I cannot find it, but if you can say, repeat it
Yeah.
live.
Yeah, I think Al, we did the train val split temporarily, right? We kind of shuffled the years of the data that we had, and then split it that way.
Actually, it's all shuffled. So both spatial and temporal, we have the same kind of distributions both in the train and validation data set. So yeah, shuffled.
Yeah, so we deliberately tried not to incorporate any geographic information into this because we didn't want, that would be a little bit too easy, right? And not really generalizable under climate change scenarios where distributions of EKE might shift geographically based on changes in wind and stratification, all the things that we think about and worry about.
Okay, thank you. So now I see some hands on my screen. Julian is first. So please, Julian.
Yes, thank you. And thank you very much for the talk and the impressive results. Actually, I have two quick questions. The first one is about if you have done some time profiling of your online inference scheme to know where you spend the most of the time, and if you think there is still some room for improvement, and where would be this improvement. And if you compare with a more standard with no smart sim, where do you spend the most time? So this is my first question. Mm-hmm. And my second question is, I'm quite a bit surprised by the fact that you use it's more technical, but the fact that you use a CNN for pointwise inference. So could you comment a bit on that? Did you try to make some to use some explanation tools to see why it improved the results, or do you think that by doing maybe a more extensive hyperparameter search you could have the same result with a traditional multilayer perceptron? So yeah, I want to have your comment on that.
Sure. Thanks. So I'll answer the first question and I'll then chuck the second one to Al. So for the first question, we did fairly extensive timing on basically every aspect of it. The data movement from the simulation to the database is actually almost negligible, right? I mean, it's a very small amount of data that's actually being moved, right? Because it's just 2D field, it's 4 2D fields. And we've got nice high speed interconnects. So the latency and the bandwidth is very low latency, very high bandwidth, right? So it's almost essentially ends up being the equivalent of doing like a full gather, right? Which, okay, fine, is expensive, but not too terribly bad. Basically all the time is spent in actually doing the inference itself. So, I don't, and like, if we look at the utilization of the GPU, it's almost at 100%. So I don't like, and if you scale the number of GPUs up and down, it basically, or scale it up, it doesn't really improve the time that much. So, it's essentially that. That's where the main cost is, which maybe is not, which is good for us, right? Because it's like inference is expensive. So then it falls to Al's job, and this is a nice segue to his question, which is like, if we really wanted to just eliminate that part of the cost of it, we'd have to find a different architecture, a smaller model. And so I'll take it away for the second part of that question about alternative architectures.
Yeah, so there were a couple of reasons why we chose a residual network, which is kind of a convolutional neural network on steroids, basically. So one was performance. So it's true, we're doing a pointwise evaluation, so it doesn't make sense to have special information built into the layers. So I took the same architecture and tried to unroll it and make a multi-layer perceptron. And actually the performance got a bad hit. So it seems like GPUs are optimized for 2D layers. And so it seems like all the functions were working way better with convolutional neural networks. We didn't do an extensive search of hyperparameter optimization. It was a bit beyond the scope of the work. Obviously, in the future work, we could do that. I'm sure that we could find a multi-layer perceptron doing exactly the same prediction, giving exactly the same results as the convolutional neural network. Because again, starting from one point, then it's all matrix multiplication. So there's no information about the neighboring points. The second reason why we chose that architecture was a bit more forward-looking. And the idea was that in the future, we might want to use patches for prediction. So use real convolutional neural networks approaches for prediction. And so in that case, we could just take out the initial part where we blow up the patch and use the same architecture and compare it one-to-one with what we got with just pointwise prediction. So these were like the two driving reasons, but I agree that mathematically there's no reason for choosing ResNet.
Thanks.
Okay, so I see Matthew is
Thank you.
willing to
Thanks
ask.
for the talk, both of you. It was a really interesting talk, really nicely explained. My main question was around timing, which you already did a great job explaining. But I guess I wanted to ask, maybe this is too technical, but when you're sending each of the nodes is sending data to the GPU, I assume you're not waiting and gathering all of those together before doing inference, but you're you're doing inference on the fly as small packets or batches of data are coming in from each of the CPUs. Is that correct?
Yeah. So essentially, if you actually look at the implementation, every single rank of the simulation calls a put tensor, run model, and get tensor. There is some batching that is done within the database so that it's not just so that it tries to do it much faster. We played around with that quite a lot, and we do find that if you do batch the results, you can get much better throughput of inferences, right? Because you're saving on the data movement and the queuing that might happen between movement of data from system memory to GPU memory. It's one of these things where individually that probably slows down, the time to completion for a rank, but overall, because this is right before like a Halo update, you kind of want to make sure that all the ranks are completing in the aggregate a shorter amount of time as opposed to individually.
Thank you. And then a second short question. It seems that as to the value you get from offloading to a GPU to do inference versus, say, doing it locally on CPU. You've got two dimensions there, right? The amount of data you need to send and receive to do that, to do the machine learning inference step versus the complexity of the model. Do you have any ideas of how the scaling of those two work? I know it's an easy question to ask, a hard question to know the answer to. It'd be really interesting to try and understand that so people can figure out whether it's worth adopting.
Yeah, so that's a really good question, and we actually have done that because it's actually really easy to say, like, should you do the inference on CPU or GPU in our setup here? It's actually on the simulation side of it that you configure that. So what we have found, which is probably not surprising, is that if you try to do inference on CPU, it's a great way to slow down your model by like 20 to 30 times, right? Because like the amount of arithmetic computations that you're actually doing is so much more than the actual, like, you know, by calling a single inference of a machine learning model, that it is just GPUs are just that much more performant actually doing inference. So you know, this is again one of the things too that we're thinking about. How can we optimize, you know, apply like standard like ML model like optimization techniques if we wanted to target CPU inference versus GPU inference. But basically on the first pass of it, if you just say CPU inference versus GPU inference, it's probably about a factor. It's a performance hit of about 20 times. So it almost mandates the need to have a GPU if you actually want to do something in a simulation.
But you're basing that just to understand. It's really good that you did the timings, but that's for your specific problem so far, right?
Correct.
You're sending 4 numbers, you're getting back 1 number, and you've created actually a relatively complex model to map between those two, right? So I guess the harder thing, but would be to understand how those two change over. Where's the crossover point for the relative complexity of model versus the volume of data. So I guess I'm thinking of my application where I want to send order thousands of floating point numbers rather than order 10 floating point numbers. Okay, super.
Yeah, I mean, and so we also have some synthetic scaling studies that where we try to just shove as much data as we can to and from. And we actually find that we scale pretty well. Like, I think I don't remember the numbers off the top of my head, but like, you know, we essentially get throughputs of something like 50 gigabytes a second, right? So we can shove lots of data through this quite easily.
Super. Thank you very much. I'll stop. I've taken too much time.
Oh yeah. Feel free to follow up with us afterwards too. Yeah, these are all good questions.
So I see a question from Chris on the chat. Maybe you want to say your question live?
Yeah, thanks. Yeah, just a quick one. And I think it's really nice that you've got an ensemble of the course model with SmartSim, and your comparisons seem to be kind of involving means, so like the zonal mean, kinetic and eddy kinetic energy, and so on. I wonder whether that might be over penalizing that kind of average. So your high resolution 10th degree truth is one realization, and might it be sufficient just to demonstrate that different metrics, different fields of the SmartSim course model lie within. So you just need like ensemble member, that would be fairly close. You just need the high res to lie within that ensemble envelope. But if you take the ensemble mean as well, then it's kind of over penalizing it possibly.
Yeah, that's a really good point. I think we've talked about doing that and think about trying to do more comparisons between the 1/10 and the quarter degree, just like as a whole. Our main issue is that we kind of threw together the 1/10 degree as a very experimental one. So we actually it's not been vetted by NCAR for, like, you know, climate purposes, especially not to the same extent as the quarter degree MOM6 one was. We kind of like looked at it and we're like, okay, do the turbulent fields look correct? As opposed to like, are we getting like Gulf Stream separation correct? Are we getting, you know, the evolution of fronts and, you know, and mixed layer depths in the Southern Ocean correct? We were mainly looking just to see, like, can we get a reasonable looking mesoscale turbulent field? And that's kind of where our evaluation of that one went. Yeah. But yeah, it's definitely an important thing, especially now that I think that GFDL actually is publishing like a 12th degree version of it. You know, we can mine that a little bit better to actually do a better resolution to resolution comparison.
Thanks. Julien? You are muted, Julien.
Yeah, thanks a lot for this great talk and for presenting those really exciting results, and with this interesting solution based on the smart sim for coupling HPC and machine learning. The question I wanted to ask is the solution you decided to adopt for this online inference is one of the several options on the table, and obviously one of the things that codes like NEMO have to decide is from the demonstration to robust production code, we need to make choices and make sure that we can take those decisions with some sort of a vision of what's going to happen with those tools. So could you comment a bit on the future plans for next or for Smart Sim in particular, in terms of the support, future development, the open source nature of it, how you approach that in HP, and maybe as a side question also, what is your plans as to the dependence to the Redis database format and things like this? That would be helpful.
Yeah, those are all very good questions. So I will say from the get-go that basically at levels of pay grades that are significantly higher than mine, they are committed to keeping the open source version alive and well. There is a separate thing that we're going on internally in terms of they want to figure out how to make money off of this, but I'll tell you quite honestly that anything that would go on relies on the development of the open source software stack. And I think if you ask any of the members of my team and all the way up directly to my director, we're very, very committed to keeping this open source, because it is an exciting area that we just want to see people actually do. And that's you can take that with as much of a grain of salt as you want, because we do come from a corporation, but as a scientist, it is open source, and we are all of us on the team are very passionate about keeping the development going on the open source side of things. And like I said, we have cover for that at much higher levels than us. And in terms of the Smart Sim project itself, it seems like we are we get mentioned quite a few times, at the upper echelon. So there is internal momentum in politics and all that to keep us going as well. So so that's what I'll say about that. We've got other plans, like I said, in mind. Once we can publicly announce them, we will. But for the open source part of it, that is kind of the commitment that we have. And also for me, personally, this is one of the reasons why I actually left my job in climate science, was to come work on this project. So that is something that I am particularly advocating for. And then with regard to development in NEMO and what that means, and MOM6 actually, this is part of my official duties, is to make sure that we can figure out a way to make this as easy for people as possible to take up and use. And as part of that, if you actually look at the MOM6 integration, the way that we actually ended up doing it was there's no reference of smart Redis at all in the MOM6 source code. We wrapped it under something that we call database comms, but you could easily also call that kind of like ML interface. And so we're trying to provide generic implementations so that people can try things like 4Pi or whatever else that to be able to use that to do those heads-up comparisons. And so that's kind of an approach that I would like to follow as well for NEMO, because obviously I'm biased, and me and Al are biased because we think we have a good solution here. But as good scientists as well, we're happy to take on the competition to try to see okay, where do we actually benefit? What are the use cases, as people have alluded to here, where it might be more efficient to take advantage of our solution versus the other ones. So that is kind of the long and the short of that answer, is that there will be support kind of going forward. If there are groups who want to do a more in-depth collaboration, like we did with NCAR, where it's Al, as a Cray engineer, did build and do the training and validation, we can talk about what that might look like. We've written proposals as co-PIs, or with some support written in on that front too. So yeah, this is something that's alive and well, and at least for the foreseeable future, we'll continue on.
Cool. Thanks a lot for this long and short answer.
Yeah.
Okay, I see no other questions. Anybody has a last point to make? Okay, so I don't think so. Well, there's been very rich discussion after the talk, so I thank you again, Andrew and Alessandro, for the talk and for answering all our curiosities. And I leave to Julian for some update about the working group activities and next step.